Hello, everyone, and thanks for joining. I'm Rich Luceni, a Red Hat Principal Solution Architect in our North America public sector covering the Department of Defense.
And I'm Tony James, Solution Architect for NASA and the Department of Energy. In this presentation, we're going to talk about edge use cases for Red Hat Enterprise Linux and how some recent feature additions enable RHEL to satisfy the requirements for remote, far edge use cases. There are a lot of terms that are used when talking about edge computing. But what does it mean at a high level? Edge computing is a distributed architecture where compute resources are placed physically close to the sources which produce and consume data. At Red Hat, we view this as an extension of the hybrid cloud. Our strategy is to enable any workload on any footprint in any location. Use cases span from simple data collection and aggregation all the way to running advanced AI/ML models to make smarter decisions in real time. The benefits of edge computing are far-reaching, but as with many things, edge computing brings its own set of challenges. In order to support these edge use cases, there are a number of challenges that need to be taken into consideration as you build out a supporting infrastructure. The first is the challenge of scale. Edge deployments, which can range from hundreds to hundreds of thousands of nodes and clusters, need to be managed in locations where there may be minimal to no IT staff, and so there needs to be a centralized way to deploy and manage them. Second, we know that no single vendor can build an entire edge stack, and so organizations need to ensure interoperability within a multi-vendor hardware and software environment. At Red Hat, we want to make sure that as edge sites scale, regardless of the physical infrastructure, they need to be interoperable with their solution. Third, edge sites need to be managed and updated in a consistent and secure way, since many are widely distributed with limited access. Looking at the different edge tiers, as we move further away from the core data center, the footprint of edge devices tends to become smaller while the number of devices increases. Imagine trying to fit a full rack of servers in a tactical vehicle out in the field, or the maintenance headaches associated with updating devices in a remote location with limited personnel. The closer we get to the core data center, these problems are easier to deal with, but at the edge, as discussed previously, there are some challenges. For this talk, the domain we're primarily focused on is land, but the content is applicable to use cases at sea, in the air, up in space, and even in the cyber realm. Red Hat offers a number of different offerings to satisfy the requirements of the different edge tiers. For environments with more connectivity, Red Hat OpenShift Container Platform offers a compelling solution for running applications in a central data center and in some edge situations with the remote worker node feature. Soon, OpenShift will even have a single node use case that may be a fit for low bandwidth and/or disconnected sites. For those environments that are dealing with space constraints and/or small form factor edge devices, Red Hat Enterprise Linux becomes an interesting option, specifically Red Hat Enterprise Linux for Edge. The remainder of this presentation will focus on the capabilities provided by Red Hat Enterprise Linux for Edge. Keep in mind that these use cases are not set in stone, and there may be situations where a different approach is needed. Red Hat Enterprise Linux for Edge was created to help simplify and secure the edge. It is the same core operating system that drives enterprises today, with a new deployment model and a set of purpose-built features that are aimed at distributed environments. So whether you need to keep existing mission-critical applications running or are feeling pressure to become more responsive with new technologies, RHEL is the proven operating system to enable your workloads. While most of this talk will focus on containers, it's important to be reminded that Red Hat Enterprise Linux for Edge also supports traditional applications that can run alongside containers. This provides flexibility in the types of applications that can be deployed at the edge. Of course, containers provide a number of benefits around portability and isolation, but traditional applications also benefit from the sandboxing and isolation provided by SE Linux and systemd. Red Hat Enterprise Linux for Edge delivers an operating system that can run any workload, and as we'll discuss in the upcoming slides, has capabilities that make it a well-suited platform for running at the edge. Our Red Hat Enterprise Linux for Edge conversation starts with Image Builder. Image Builder has both a web-based user interface and a command line interface. Blueprints are a core component of Image Builder. A blueprint describes things like which packages and their versions will be included in an image, as well as additional customization options for things like adding users, starting services, opening firewall ports, and more. With the release of Red Hat Enterprise Linux 8.3, the backend of Image Builder was migrated from Lorax to OS Build. Along with this change, we added support to Image Builder for generating what we call RHEL for Edge commits using RPM OS tree. The standard RHEL for Edge image contains the core package group and podman, which results in a small base install with the ability to run containers. Additional packages can be added based on user requirements. If you're not familiar with RPM OS tree, we'll be talking about it next. RPM OS tree is the base of what makes Red Hat Enterprise Linux for Edge an immutable operating system that is suitable for far edge deployments. RPM OS tree is an imaging and packaging system that provides transactional updates, with updates being staged in the background and applied upon reboot. This eliminates those in-between states where an update does not fully complete due to something like a network interruption. Previous update images are maintained so that a system can be reverted to a previous image with a simple reboot. The OS tree library is a core component of RPM OS tree. OS tree performs atomic upgrades of file system trees and is often compared to Git because of its content-addressed object store model that uses branches to track file system trees within the store. All files in the store are checksummed, which provides an additional level of integrity. Provisioning a Red Hat Enterprise Linux for Edge image uses the familiar Kickstart technology that has been leveraged for many years by system administrators to deploy RHEL. Outside of the customization options that are provided by Image Builder blueprints, Kickstart provides an opportunity to further configure systems pre- and post-install. With the release of Red Hat Enterprise Linux 8.4, Image Builder can generate RHEL for Edge installation media for situations where Kickstart is not the desired approach. Installer configuration can be embedded into the installation media for automated offline installs. Red Hat Enterprise Linux for Edge updates are created via Image Builder by generating additional RPM OS tree commits. Providing access to these updates is as simple as hosting the commits on any web server. This simplifies the requirements for the infrastructure that will distribute updates and provides additional flexibility. With the automatic update policy setting set to stage, clients will periodically check the web server for available updates and stage them to take effect during the next reboot. Many edge locations have limited connectivity and bandwidth. With RPM OS tree, updates are optimized to send only new content rather than a complete operating system image. For situations where an administrator is not around or available to monitor the reboot of an edge device after an update, we created GreenBoot. GreenBoot is a health check framework for systemd. These health checks run as part of the boot process and can trigger an automated rollback to the previous RPM OS tree image based on whatever conditions need to be met for your OS or application workloads. Example health checks can include things like simple DNS resolution or ensuring that a containerized service starts successfully and responds to a command. Last but not least, Red Hat Enterprise Linux for Edge includes the Podman container engine. Podman is not new and has been around for many years in Red Hat Enterprise Linux. It brings the ability to run standards-compliant containers with a daemonless architecture. Containers can be run in rootless mode which improves the overall security posture of the deployment. With Podman, containers can be managed with systemd, which brings scheduling and process monitoring benefits, and, through socket activation, the ability to scale from zero in a serverless fashion. Security and trust come from an immutable operating system image that also has a unique identifier which simplifies auditing and tracking of distributed deployments. Maintenance is greatly simplified when atomically updating distributed remote deployments, significantly lowering operational costs. Red Hat Enterprise Linux for Edge helps meet the challenges of edge computing. Before we dive into the demo, I'd like to set the stage and talk about what you're going to see. Redundancy at the edge is often a requirement. For this demo, you will see two systems that are running Red Hat Enterprise Linux for Edge with a virtual IP that will send traffic to a primary node and fail over to a secondary node as needed. When traffic is received, we're using a capability of systemd called socket activation that will start a container to service the request. Additionally, various activities like upgrades and updates are triggered by systemd timers that launch similarly named services when conditions are met, like timer expiration or some amount of time after reboot. Virtually any condition or interval can be set within a systemd timer, covering a wide range of use cases. Without further delay, I'm going to hand it over to my colleague, Rich Lucenti.
Hello again. So I'm going to walk through the RHEL for Edge demo for you. But before we get started, I want to quickly orient you with what you'll be seeing on this screen. So we will switch between these terminal windows as well as a web browser, but for the terminal windows, they are organized in a specific pattern. In the upper left, we have the host server window. This is where I'll issue most of the commands to direct the demonstration for you. Below it, you have a web server window. This is a simple web server that will provide the content necessary to both install and upgrade our two edge devices. The two edge devices will be running as virtual machines and their serial consoles will be directed to the windows on the right. Let's take a look at the blueprint file that fully describes the operating system images we're going to build. So here you'll see that we can have some metadata describing these images, giving it a version, a name, things like that, as well as detailing the packages that should be included, and then any customizations like firewall settings or adding new users. We'll use the command line tool to push our blueprint file to our image builder server so we can use it to compose our operating system images. The command line tool can be used to show the various compose types. Here we see the different types of operating system images we can build, including AMIs, VMDKs, but for this demonstration we're going to focus on RHEL Edge Commit. These are the types of images based on OS tree that allows us to atomically install and upgrade our edge devices. We'll start the image compose by giving it both the blueprint name and the image type that we would like. Later, we'll use the unique identifier for this compose to download the content for our operating system image. We can monitor the status of our job while it's running. An image can typically take between 5 to 10 minutes to complete, but in the interest of time, this video compresses long-running processes. Now that our compose is finished, we'll create a directory and we'll download the operating image content to it. We'll use this directory later to provide the content necessary to install our edge devices. Expanding the image archive enables us to examine the JSON file that has metadata about our image. You'll notice that there are two key values here. OSTree commit uniquely identifies the image, and ref identifies the branch for our image content. OSTree image content is not human readable. You can't, for example, list the directories to find what packages are there. However, we can use the RPM OSTree utility combined with the reference to see all of the packages in our image. Piping the output of RPM OSTree to grep shows us that the strace package is not a part of this operating system image. We're going to add that package when we build a child operating system image based on this one. We need the OSTree commit identifier for this image to designate it as the parent of a child operating system image, which we'll build later. We'll copy that value to the clipboard. The web console included with RHEL 8 supports multiple plugins. We're going to use the image builder plugin to compose our child operating system image. You can add additional sources for RPM packages. Base OS and AppStream are included by default and they cannot be removed, but you can add as many additional sources as you need. Drilling into our blueprint file, we can add additional users via the Customizations tab. We can add additional packages to our operating system image via the Packages tab, and we can also see what images have been built via the Images tab. We'll select the Edit Packages button to go ahead and add the strace package to our blueprint. Each image type includes a core set of packages, plus additional packages specific to that image type. You cannot change or remove that base set of packages. However, any additional packages that you add to your blueprint, you can then remove later if you desire. Changes to a blueprint file are pending until committed. We'll start the compose of our child image by selecting the RHEL for Edge image type and then pasting in the parent's OSTree commit identifier that we previously copied to the clipboard. Again, these builds can take between 5 to 10 minutes to complete, but no one wants to watch grass grow, so I've seriously compressed time here. We'll create a version 2 directory to hold the contents of this child compose. In order to download those contents, we have to get the correct identifier for them. Like before, we'll expand the content, examine the metadata, and then also confirm that the strace package is included in this operating system image. Returning to our original operating system image content, we're going to run a simple web server to provide that content to the edge devices during installation. The web server maintains a running total of all the files requested as well as their cumulative size. We'll use that to compare to how much data is downloaded during an upgrade later. Each edge device is installed and then after installation is complete, rebooted. During both the install and the reboot, all of the console output is redirected to the terminals. You'll notice in the web server that each edge device downloaded just under 30,000 files and roughly 600 megabytes of content. We'll look for running container applications on each edge device, but you'll notice right away that there aren't any. Each device is using systemd socket activation to listen on port 8080. When a request is received, systemd will start a container via podman to service the request. Additionally, a virtual IP address is being managed by the edge devices using the virtual router redundancy protocol. If the device holding the virtual IP should fail, the other device will handle requests sent to that virtual IP. curl is used to send an HTTP request to the virtual IP address on port 8080. One edge device will receive the request and spin up a containerized web server to respond. The other edge device remains idle. Now we'll destroy the edge device that originally responded. The virtual IP address will move to the other edge device, and it will spin up a containerized web server after curl sends the request. The edge devices are also configured to use Podman Auto Update. If we pull all the web server container images, you'll see that the production tag, PROD, matches version 1 of our web server container image. We'll change the production tag to match version 2 and push that to our registry. A systemd timer on the edge device will trigger Podman Auto Update to run. Since there's a change to the container image in the registry, Podman Auto Update will stop the currently running container, pull the container image from the registry, and restart the containerized web server. When we send an HTTP request, we now see the content from the updated container web app. Moving over to the running edge device, we can demonstrate the resiliency of systemd and Podman. Here I'm killing the containerized web application. Restart conditions can be defined in systemd policy. As you can see here, the terminated container web application beginning with ID F503 is replaced by systemd with a new container having ID A239. RHEL for Edge provides the green boot facility to determine if an operating system upgrade is successful or needs to roll back. Several directories under etc green boot define the various conditions. The check required.d directory contains scripts that must succeed. The check wanted.d directory contains scripts that should succeed. Green.d and red.d contain scripts to run after success and failure results, respectively. The rpm-ostree command shows the operating system images on the device with the active image denoted by an asterisk. Each image has a unique identifier. To simulate failure of an upgrade, we use a contrived check script to capture the identifier at first boot and then the identifier with each successive boot shown here. Since the script remembers the original identifier, any attempted upgrade will fail and roll back. Later, we'll remove the original identifier file so the upgrade can succeed. Our simple green boot check script returns a pass-fail result on whether the two identifier files are the same. You can review the script here. Let's go ahead and attempt an atomic upgrade of the operating system. First, we'll switch our simple web server on the host to offer the version 2 content to the edge device. Next, we'll review the systemd timers that trigger systemd services to run. These timers support nearly any condition or interval desired. The service to pull updated content is triggered to run once per hour. Rather than wait that long, we'll initiate it manually to download the updated OSTree content and stage it on the edge device. Notice that very little data was downloaded for the upgrade since the edge device already has the content for the version 1 parent operating system image. A separate systemd timer on the edge device triggers a reboot when there's a staged update. On the boot screen, OSTree:0 represents the new operating system image, and OSTree:1 represents the previous image. Since the green boot check is configured to fail for this demo, RHEL for Edge will make 3 attempts to upgrade and then automatically roll back to the previous operating system image. Green boot checks can be used to ensure that all necessary conditions are met for both the operating system and any desired workloads. Let's log back into our edge device and confirm that the upgrade, which includes the package strace, was not installed. Examining the commit identifiers also confirms that we're still running the version 1 operating system image. Deleting the file with the commit identifier will allow the green boot check to pass and the upgrade to succeed. Let's once again manually trigger an upgrade. You'll notice that only 5 files of negligible size were requested since we already have the upgrade content on the edge device. This time the content is simply being restaged. A systemd timer triggers a reboot since there's staged content, and once the system is started, we can log into the upgraded edge device. We confirmed that the upgrade was successful by seeing that the strace utility is now installed and the commit identifier for the active operating system has been updated. We demonstrated how RHEL for Edge, Podman, systemd, and keepalive-d enable a serverless container application to be started via socket activation, the automatic failover from one edge guest node to another, the automatic restart and update of a containerized application, and an atomic upgrade of the underlying operating system with rollback on failure. All of the content for this demo is available at the following URL. Thanks for watching.